And now we can say, okay, we are experts in Gauss's law, so now we know how to apply it for in a different situations, right? So we know all the properties of the Gauss's law, and now, of course, we will start applying it everywhere it's possible, right? It's sort of like a if you give a kid scissors, right, then everything in the house will be cut in pieces, right? So we are pretty much in a similar situation, right? So now we have a new tool, and of course we're going to stick it everywhere it's possible, right? Okay, and we're going to use Gauss's law today a lot to explore properties of conductors. We need them. We need them a lot. Of course, in the electrostatic equilibrium. Of course, we will define all that in a second, right? Okay, it's still chapter 24. Yeah, these are sections. So first of all, we usually have three types of materials. Most likely you're familiar with those, right? So we have dielectrics, right? We have conductors, metals, right? And we have semiconductors. So semiconductors have tons of amazing properties, right? And that type of material deserves a separate course. And at some point, some of you will have courses about semiconductors, and you will learn about those amazing properties. All our electronics is based on their work, right? But in this course, we're only interested in insulators or dielectrics and conductors or metals. So first of all, we need to see the major differences or major difference between these two types of materials, right? And then as a result, using this major difference, we can add additional properties of conductors, because we will need most of the time conductors, right? Okay, so first let's start with an insulating material, insulator or dielectric, right? It's that material where it's difficult to create current, or almost next to impossible, right? Right. So what happens? Let's recall classical model of an atom where you have what? Nucleus at the center, right? Which is positively charged, and then there is a cloud of electrons orbiting around that nucleus, right? And electrons which are closer to the nucleus, they are called core electrons. And on this picture, it's basically piece of a dielectric, and of course it consists of tons of atoms, right? And if you take one of these atoms, for example this one, you see at the center there is a red dot. That is a nucleus, right? And around the dot there are two circles, dark green and light green. Dark green represents core electrons, electrons which are closer to nucleus, right? So those core electrons, and electrons which are farther away from the nucleus, right? They are called valence electrons. Again, you see that those electrons are represented by those that light green color. Okay, so in a dielectric or in an insulating material, all those electrons, core electrons, valence electrons, they're all tightly connected. They're all tightly bound to nuclei, overall nuclei, right? As a result, basically, like they are prisoned, right? They cannot escape from their nucleus. Okay, not prisoned, probably they're sitting in their families, right? Right, and they don't go outside. Basically, as a result, this space between atoms, you see, we have tons of atoms, and space between them is gigantic. Lots of empty space, right? And that empty space is free. There is nothing. There are no free electrons. As a result, if you apply potential difference across a dielectric, there are no free electrons to travel, to create a current. Right? Yeah, the most what you can do, you can slightly distort these atoms, so electrons, maybe clouds of electrons can be slightly elongated in a certain direction, but that's the best you can do, right? So that's why it's difficult or almost next to impossible to create current in an insulating material, because there are no free electrons. They are all connected to their nuclei. Now, what about conductors or metals? It's a second situation, right? This picture. In this material, those valence electrons, right? You see valence electrons, those which are farther away from nuclei, they are weakly connected. They are weakly connected to the nuclei. And as a result, you can just slightly increase temperature over this metal, for example, from an absolute zero, right, minus 273 Kelvin, right? As a result, lots of those valence electrons will get loose and start drifting and start become free. They become free, right? And fill up that space between atoms. Even if you just sneeze maybe on that piece of a conductor and a few additional electrons will appear, will become free, right? As a result, these metals has tons of free electrons. And as a result, if you apply potential difference across piece of a conductor, of course, those electrons, free electrons, will respond immediately and they will start drifting in a certain direction, giving us what we call current. So that's why it's so easy to create current in metals. And of course, we use metals in our circuits, right? Because we can create current because of those free electrons. So as a result, the major difference between insulating material and conducting material, metal, that conductors have tons of free electrons. They are free to move whenever they feel like traveling, right? But in insulating materials, no. Okay, so now, knowing this major difference, we should be able to add additional properties of conductors. So now let's start moving, getting those additional properties of conductors. But again, this is the major difference. Right. Okay, so first, and since we just introduced Gauss's law, you can guess that most likely we're going to use Gauss's law in this lecture a lot. Okay, let's say a few times. Right. So first of all, let's imagine this situation, right? Just for fun. Let's take a piece of a conductor. Again, we're going to talk about conductors today only, right? A piece of a conductor, let's assume that this slab of material, piece of a conductor, and let's assume it is electrically neutral. What does it mean electrically neutral? It means it has equal number of positive and negative charges. So as a result, overall, it's electrically neutral, right? And just for fun, let's expose it to some external electric field. For simplicity, I drew a uniform electric field, right? I know maybe this external electric field is created by some gigantic capacitor, right? Maybe over here there is a positively charged surface plate. Over there somewhere there is a negatively charged surface. As a result, we have this uniform electric field, and there is a conductor inside. And so now our goal to see what happens to this conductor if you expose this conductor to this external electric field, right? And we just need to know only the major difference between the major property of a conductor. It has tons of free electrons. So what do those what are those electrons going to do? What will be their response to the presence of this external electric field? Of course, the question reasonably simple. Let's imagine this is an electron inside of this conductor. Okay, barely visible, right? And of course, this electron is going to interact with this external electric field. And it is going to experience what? Electric force. F equals QE. You remember that fundamental equation. F equals QE. And since electron is a negatively charged object, electric force is going to point which way? Direction is going to be opposite to the direction of the external electric field. So it will be towards me, right? So the electron is going to start drift, is going to travel this way. in the direction opposite to the direction of the external electric field, because it's a negatively charged particle, electron. So as a result, electrons are going to travel to this side of the plate, giving us, and of course they cannot jump over the border, right? We have a strong border control, right? So of course they're all going to be accumulated on this side of the conductor. And of course, since the conductor is electrically neutral, if we have excess charge of excess of negative charge on this surface, there must be positive charges on that side. So positive charges will be left behind. Okay, so now the question, of course, logical question. How many electrons are going to travel to this side, to this border, right, to this side of the conductor? 100, 1,000, 5,000, I know, millions, all of the electrons, right? And of course, you understand that the question actually is not about how many electrons will travel. Of course, the question is actually slightly deeper. Of course, the question is about the mechanism which is going to stop electrons from moving to this side of the conductor. What is the mechanism? At which moment electrons are going to stop drifting to this side of the conductor, leaving behind positive charges? Some students know that, some don't, and it's normal. Look, let's try to see what happens to this conductor once you first expose it to this external electric field. Okay, so we have first you put the conductor and position it inside of this external electric field. Of course, electrons start drifting, right? Giving us these negative charges and positive charges. What do these negative charges and these positive charges, what are they going to create? Can you see that? Look, physically, it looks like looks like a capacitor. So here we have a negatively charged surface, right? And here these positive charges creates like a positively charged surface, right? So we have a surface of negative charges, a surface of positive charges. What are they going to create? They're going to create their own electric field, blue electric field, internal electric field. This charge separation, it's called, basically it's called, we polarize the conductor, right? We induce charges. So these charges create their own internal electric field. And what's the direction of this internal electric field? Of course, from plus to minus, from positive charges to negative charges. So you see, this blue electric field is going to point in the opposite direction to the direction of the external electric field. So inside of the conductor, they battle, they fight, right? So external electric field that way, internal electric field in the opposite direction. And now, as I told you, let's just see what happens in time with these electric fields. So first, let's assume that a few electrons traveled to this side, right? So now a few electrons over here, a few positive charges over there, and internal electric field is reasonably small. A reasonably small internal electric field. Let me represent it with my finger, right? But external electric field is strong. So as a result, inside of the conductor, of course, this strong electric field is going to win, right? And of course, the net electric field, so basically net, it means you need to add this red field and blue field. Of course, net electric field will be still that way. And the electrons inside of the conductor, they still going to feel electric force, and they're still going to travel towards this negatively charged surface, right? So more electrons drift to this negatively charged surface, right? And as a result, it means that blue field, this blue internal electric field becomes stronger, right? So again, they battle, they fight with this external electric field. As a result, net electric field becomes somewhat smaller, but still not zero. It means electrons still feel the electric force and still travel, increasing internal electric field. But if it's still smaller than external electric field, that electric field still not zero, and electrons still feel the electric force, and they keep traveling. So those electrons will keep traveling and traveling, keep drifting until what? Until internal electric field and external electric field equals to each other in magnitude, but of course they're in opposite directions, point in the opposite directions, right? As a result, what's the value of the net electric field at that moment when these two fields are equal? Electric field will be zero. And what will be the response of electrons once electric field becomes zero? They will stop traveling because now they're not going to experience electric force. And they were traveling because they were pushed by the electric force. But now, once electric field is zero, they will stop experiencing electric force and they will stop traveling. So charge separation at that moment will be stopped. Electrons stop moving, electric field zero. Yeah, as I said, electrons stop moving. They basically like get settled, right? Buy house, right? Get married and live happily ever after at that moment. They settled, their life is done, life is great, right? Electric field is zero. Right? So pretty much electrons will stop traveling when the electric field is zero. So at this moment, when this happens, electric field zero and electrons stop traveling, these conditions are called electrostatic equilibrium. Electrostatic equilibrium. Of course, you have to wait for a short period of time. Once you grab the conductor and expose it to external electric field, you will have to wait for a short period of time, maybe microsecond, maybe nanosecond, maybe picosecond. It depends on the material, it depends on mobility of electrons, but you need to wait for a short period of time because it will take for electrons some time to run like crazy, right? Trying to make an electric field zero, right? And once they manage to make electric field zero, they get settled, yeah? And now the conductor is in the electrostatic equilibrium. So pretty much the job of electrons in this situation, they will keep running and running and running with the goal to make electric field zero. Otherwise, they will never stop running because they will experience electric force. That electric force will drive them crazy, right? Will keep pushing them. So that's what happens over here. But of course, and so from, okay, let me open a few. All right. So from now on, we're going to discuss conductors from time to time. And most of the time, we're going to assume tacitly, or it will be stated that conductor is going to be in the electrostatic equilibrium. So again, at that moment, electrons stop traveling, right? And electric field is zero. So the second major property of a conductor. In the electrostatic equilibrium, electric field inside of the conductor is zero. Right, again, otherwise electrons will keep drifting, keep moving, right? Okay, it's not a proof. It's more like a justification of this fact that electric field inside of the conductor is zero. So we need to remember. So now we know two properties. Tons of free electrons inside of the conductor. And in the electrostatic equilibrium, electric field is zero. Again, electrons, like brave soldiers, they will keep running and running, or athletes, and they will keep running until the electric field becomes zero. Right. Okay, so now next, what if, okay, in the previous situation, a piece of a conductor was electrically neutral. Basically, we had equal number of positive and negative charges. Now, let's make situation slightly more complicated. Let's take a piece of a conductor and dump some amount of, for example, positive charge on that piece of a conductor. All right, so let's say we have a piece of a conductor, and what if we, for example, at this point, dump some amount of positive charge? And now it makes sense to ask the logical question. Where does this, of course, it's excess charge, right? We added that additional charge. Where does this excess charge reside in this conductor? Right? A reasonably logical question. So let's ask that question, right? And let's try to answer that question now. So now it's not electrically neutral piece of a conductor. And again, we're going to discuss the situation. So we wait for a short period of time, right? Because who knows, for a short period of time, it will be a mass inside of the conductor, like in the previous slide, right? First, for a short period of time, it was a mass, electrons were running like crazy, right? And we are going to wait long enough so that conductor reaches what is called, again, electrostatic equilibrium, right? And now, in the electrostatic equilibrium, we want to know where does this excess charge reside inside of the conductor, right? Okay, so now maybe you know the answer, but let's actually prove or show, yeah, where the charges are going to be. And you know what? Guess which law I'm planning to use to show this property. Since we just introduced Gauss's law, most likely that I'm talking about the Gauss's law. So let's apply Gauss's law to see locations of these charges. Right. Okay, so first of all, you remember whenever you want to use Gauss's law, what do you have to do first? You have to pick a Gaussian surface. Again, any surface can be used, right? Any surface can be used. All right, so I know, my soul desires, secretly desires to pick a Gaussian surface just below this surface of a conductor. Why not? I can apply it, right? Gauss's law is universal law, and it can be applied for any Gaussian surface. Okay, so I want to pick this Gaussian surface. Nothing and no one can forbid me from doing this. Okay, so now Gauss's law, right? We used it already a lot. And now look, so again, on this side we have a flux. There we have Q enclosed divided by epsilon naught, and of course, you see Gaussian surface. Can you tell me, what's the value of this electric flux? What's the value of this integral? Can you see that? What will be the value? Again, you remember I told you that we waited long enough to make sure that a conductor now is in the electrostatic equilibrium. So what will be the value of this integral? Okay, if you're not very confident, okay, let me push you. All right, so this Gaussian surface, and of course the integration is done over the Gaussian surface. Yeah, it's slightly below the surface, but it is inside of the conductor. All right, it is inside of the conductor. What's the value of the electric field inside of the conductor in the electrostatic equilibrium? We just discussed in the previous slide, right? It's zero, right? Electrons stop running, right? So their job is done. So they manage to reach their goal, right? Electric field is zero. So if electric field is zero, that the value of the electric flux will be zero because you integrate over the surface where there's no electric field. So electric field is zero, and as a result, our flux must be also zero. So it means that Q enclosed is zero. It means that Q enclosed is zero. Again, what is the meaning of Q enclosed? It's a charge inside of our Gaussian surface. And inside of our Gaussian surface, it's the internal part of the conductor. So immediately we conclude, so it looks like in the electrostatic equilibrium, it's impossible for the excess charge to be inside of the conductor. Nature forbid it, right? So we conclude that inside of the conductor, it's impossible excess charge. It's impossible for the excess charge to be. Of course, there is a charge inside, but it's an equal amount of positive and negative charges, right? So overall, internal part of the conductor is electrically neutral. We're talking about the excess charge, right? So we dump that a positive amount of charge. So now, if it's impossible for that excess charge to be inside of the conductor, where else it can be? There's only one place for them left to exist, right? On the surface. Okay, just below the surface, just outside of our Gaussian surface, right? So pretty much all that excess, positive excess charge can be only on the surface of the conductor. So now, again, it's in the electrostatic equilibrium, right? In the electrostatic equilibrium. So now we got the third property of the conductor. The first one, tons of free electrons. Second, in the electrostatic equilibrium, electric field inside is zero. And again, in the electrostatic equilibrium, any excess charge can reside only on the external surface, on the external surface, right? In this case. And conceptually, logically, it's actually easy to see, because you remember, if you dump positive charges, for example, at this point, right? So what are those positive charges going to do to each other? They hate each other, right? They repel each other. If they repel each other, of course, they're going to run as far as possible from each other, right? And so what are the farthest points on the conductor? Of course, the surface. Of course, these positive charges are going to distribute themselves somehow in a complicated way along the surface of a conductor, trying to be as far as possible from each other, right? It's a simple explanation, right? So, all right, now we got this information. So now next, um, so now we know basically almost everything about the conductor inside. Again, what do I mean everything? We have only two basically parameters, charge and electric field, right? So now we know that electric field inside of the conductor is zero. And it's impossible for excess charge to be inside of the conductor. It can be only on the surface. So basically inside of the conductor, it's a picture is clear for us, right? So now let's step outside of the conductor. Okay, we cannot talk about charges outside of the conductor because they are not part of the conductor, right? So, but what about electric field just outside of the surface? Yeah, that's a reasonable question to ask, right? So what about electric field just outside of the conductor? What can we tell about that? Okay, so of course, we need to assume that a conductor is charged. Again, we're going to assume that it is in the electrostatic equilibrium, because if it's not in the electrostatic equilibrium, it's a mess, right? Again, we assume that we waited long enough. Why does it have to be charged, a conductor? Because if it's not charged, then of course the electric field outside will be zero. Object must be charged in order to have non-zero electric field outside, right? So that's why, of course, we assumed that the conductor is charged. It has excess positive amount of charge, and of course we know where the charge can be only, right? On the surface. You can see positive charges are distributed, in this case uniformly, along the surface of this conductor. And of course, electric field inside is zero again, electrostatic equilibrium again. At that moment, electrons stop traveling, stop drifting. You remember, they get settled, buy house, get married, and live happily at this moment, right? So now, what about electric field just outside of the surface? We're going to use the proof by contradiction. And so as a result, we just need to state the right statement, right? And then try to prove it. So electric field outside of the conductor, just outside of the conductor, is perpendicular to the surface. Actually, the first lab during the normal semester, when we had real physical labs at school, students had to map electric field and they had to see it experimentally. Right? But in this case, yeah, life slightly different. So electric field is perpendicular. Let me draw it, right? And now let me give you a proof by contradiction. Again, the key word conductor is in electrostatic equilibrium, and electrons at that moment do not travel. They do not move. They settled, right? So now, what if we assume, okay, proof by contradiction, let's assume that there is a component of the electric field tangent to the surface. If there is a component of electric field tangent to the surface, what will be a response of electrons if there is a component tangent to the surface? What will be the response of electrons? They will start experiencing electric force, right? And there is a space where they can travel along the surface. If there is a component tangent to the surface, electrons will start moving, start traveling. But we assume that conductor is in the electrostatic equilibrium. It's impossible, right? So if there is a component tangent to the surface, it means that conductor is not in the electrostatic equilibrium. If a conductor in the electrostatic equilibrium, it's impossible for a tangential component of electric field to exist, right? Of course, you can say, so how come that electrons do not travel because of this component of the electric field? Because this is the border. They cannot cross the border, right? There is a wall built. Build the wall on the border, right? So that's why this component can exist and electrons do not travel, because they cannot. Okay, so now we added additional property, electric field just outside of the surface of a conductor, again, in the electrostatic equilibrium, is perpendicular. Right. Okay, so now basically we know almost everything. Now I think there will be a quick clicker question. No. Okay, so next logical question. What about the expression for the electric field outside? Electric field strength. This is the derivation. I'm not going to derive it. If you want, you can read it again using Gauss's law. And electric field just outside of the conductor, just outside of, above the surface of a conductor, is proportional to the surface charge density of the conductor. Here, of course, there are distribution of charges, some along the surface. Of course, you can introduce surface charge density. So eta divided by epsilon naught, that's how you can find electric field strength just outside of the conductor. I think in your homework, at least during the normal semesters, I gave that problem. One of the problems related to this formula. Basically, I think there is a coin, piece of metal, right? And the electric field above the coin is given. And the question asked about, I think, surface charge density. So using this formula, it's a piece of cake to find it, right? I need to check. I think I assigned that problem. Okay, so yeah, we're not going to derive it, right? Okay, question for you. Quick, before we go, before we call it today, we still have 3 minutes. So what do we have here? Again, the poll is in the chat. And today you were not active in the chat, so it must be right there. So let's assume that we have a electrically neutral piece of metal. Before school got closed, I took with me some props, right? So we have electrically neutral piece of metal. Then we take a positively charged point on some object and position it, you see, like in the picture, at a distance r small from the center of the sphere. We position this positive charge. Of course, this positive charge, r capital, it's a radius of the sphere. Of course, this positive charge creates its own electric field, which fills up the whole space. We know that. So now, in the presence of this electrically neutral piece of metal, what will be the value of the electric field, net electric field, at the center of this sphere? Give it a try. And you see the answers, right? A, B, C, D, and E depends on what the metal is. Interesting option. So give it a try. Yeah, I didn't expect this distribution of answers. Okay, we're not going to wait any longer, right? Because students might not be here. The answer is very simple. Again, we assume all the time that we wait for a short period of time until the conductor reaches electrostatic equilibrium. And you remember what almost the first slide of today's lecture, we spent like 10 minutes discussing that in the electrostatic equilibrium, what will be the value of the electric field inside of the conductor? Zero. Those brave electrons, they will never stop traveling, drifting, all right, until they will make electric field inside of the conductor zero. If they cannot make it zero, if the electric field outside which they want to compensate is so strong, basically at that moment, most likely you just explode the conductor. But of course, we're not going to talk about those extreme situations. What happens in this case? Positive charge, of course, it creates electric field everywhere. But it's not the only electric field. Yeah, this positive charge creates electric field inside of this piece of metal. But at the same time, electrons see that electric field, and of course they start traveling. Where will they travel? Of course, they will travel to this side of the conductor. On this side of the conductor, okay, let me draw it this way. On this side of the conductor, right, there will be accumulation of negative charges. And of course, that side of the conductor will be positively charged. Why? Because in that case, they will create internal electric field, which is going to cancel this electric field inside. So like on that slide, on the first slide, you remember that red electric field, blue electric field, and they battle inside. The same situation here, but of course geometry is more complicated. Red external electric field is created by this positive charge. And then blue electric field will be created by those induced charges on this surface and that surface. Again, there will be battle, and of course, sooner or later, electrons will create strong enough electric field, internal electric field, and as a result, the net electric field will be zero all the time. Unless I told you if you create very strong electric field, external electric field, but in that case, most likely electrons will start just jumping out of the conductor, just basically exploding, right? But under normal conditions, in the electrostatic equilibrium, electric field inside will be zero. Nothing to discuss. Okay, guys, so remember, in the electrostatic equilibrium, electric field inside, net electric field inside of the conductor must be zero. Electrons will, like brave soldiers, they will go to the borders and do their job, right, to make the net electric field zero. Let's make the system more complicated. What if it's not just a solid piece of a conductor of some complicated shape? Let's assume that there is a hole inside, a void basically, which doesn't have connection, physical connection with the outside world. All right, so it's somewhere deep inside. And what if we charge this conductor with a hole? For example, let's say this is our piece of a conductor, it's charged. And now let's assume there is a hole inside of this conductor. And since this conductor now is charged, right? Before, without a hole, you remember, charges could be or can be only on the external surface. Now we have two types of surfaces. We have this external surface, right? And also there is an internal surface. And of course, logical question. So now we have an excess charge, or the excess charge in the conductor. And logical question, are there any charges on this interior surface? All right? Are we going to get any charges on this surface? Completely logical question. And in order to answer this question, guess which law we'll have to use one more time? Yeah, Gauss's law. So let's apply Gauss's law. And of course, you remember whenever you want to apply Gauss's law, first of all, you have to pick a Gaussian surface. So let's pick one. And you remember you can pick any surface you want. Okay, I want to pick the surface which is just above this interior surface. Every time at this moment I kind of pause because I don't know how to say it correctly. Is this surface just above this interior surface? or below this interior surface. I don't know which way, which way of saying is the correct way. Right. So, but anyway, so this is our Gaussian surface, and let's apply Gauss's law. So here's the Gauss's law, right? Electric flux equals to Q enclosed divided by epsilon naught. And guys, again, we assume that we waited for some short period of time, so this conductor is in electrostatic equilibrium. So guys, can you tell me what will be the value of this flux, the value of this integral? Number. At this point, probably you already know the answer, right? It will be 0. Because because this Gaussian surface, because the Gaussian surface is inside of the conductor. Yeah, it's just above the interior surface, but still it is inside of the conductor. And I already mentioned to you several times that electric field inside of the conductor is 0. So basically we're integrating a 0 function over that Gaussian surface. Since electric field is, okay, let me show first in the conductor, electric field is 0, right? So integrand in our integral is 0, and of course flux is 0, and as a result Q enclosed, charge enclosed within our chosen Gaussian surface is 0. So it means what? It means that it's impossible, according to the laws of nature, to have any excess charge on the interior surface. Right. So if there is a hole, charge is not going to be there. So any excess charge in this case still will be on the exterior surface, external surface. Okay, so now that's another property which we need to remember. And now, sort of like a consequence, very important. Look, guys. So, electric field inside of the conductor, again, electrostatic equilibrium, blah, blah, blah. Electric field equals 0. Then, around this void, around this hole, interior surface doesn't have any charge. What can you tell about the electric field inside of this hole? I think the answer is obvious, right? The electric field will be 0, right? Can you think of any important application of that fact, of this fact, that electric field inside of this hole is 0? Very important conclusion, which can be used and which is used a lot in our world of applications, right? And most of you know that. Okay, let me check the chat. Okay, about the exam. No, the exam will be for 50 minutes, first half of the class. Okay, I will give you most likely like 1 hour. Because during the normal semesters, midterm exams are 50 minutes exam. Okay, so back to the application. So this, okay, so electric field is 0. Obvious application. Let's say you have a piece of equipment which is sensitive to external fields, electric field. And let's say you don't want your device to be exposed to that external electric field because maybe it distorts your measurements, right? So what can be done? You can take a piece of metal, make a hole inside, put your equipment in that hole, and it will be protected from the external influences, right? It's a Faraday's cage, basically, right? Shielding of the equipment. And of course, it is used a lot, right, to protect the equipment. And of course, quite often, it doesn't have to be a solid piece of metal. It can be metal mesh. Sometimes it's enough. Of course, you have to calculate properly, right? Because like in one of my demonstrations in the again when we were at school, I would bring my phone, right? wrap it with just aluminum foil, and usually ask student to give me a call, right? And of course, call did not. Of course, the call didn't get through. And you know what? Once I embarrassed myself, right, to some extent, right? So I practice in my office, right, Olney Hall. And if you know, Olney Hall has a very thick walls, right? So as a result, a cell phone signal is reasonably low, weak, right? So I practice, yeah, I tried to call myself from the stationary phone, and of course, call didn't go through. So I was confident, went to the class in Olney 150, and their walls not as thick, right? And the building is isolated, like small building. And so I asked student to give me a call. And my phone started ringing, right? Of course, the whole class, right? A few hundred students started laughing at me, right? So I should have wrapped it into aluminum foils, right? Because yeah, if the signal is strong, of course, you need to calculate properly to make sure that Faraday's cage work, right? So you have to be careful. And another example of this application of this, uh, in one of I think it was the final project before I went to defend my PhD here in one of Lancet Mills, the lab, STL. All right, and we were running some experiment. And there was some optical experiment, but after a few down conversions, my final signal was very low and not far from the frequency of our school radio station, right? And the antenna of school radio station was on Foxhole, and the building is in I was in Lancet. Of course, that signal was very strong, right? So at those days, right, I hated school's radio station, right, because it was affected my measurements, right? So, and I remember my advisor at some point suggested, maybe we can build a Faraday's cage around optical setup, right, to sort of protect the equipment from the influences of school's radio station, right? But we didn't build the cage because we just managed to use filters and filter out, because there was some frequency difference between my frequency and the school's frequency. So we managed to filter that out. Right? But Faraday's cage would be one of the solutions, right? Okay. Um, for example, okay, let me bring slides forward. Right. For example, let's say, so here you see uniform electric field. So right now it's a nice uniform electric field. And let's say we want to get rid of the electric field in this part. I took this picture from the book. All right. So you take a solid piece of metal, made a hole inside, right? And as a result, yeah, electric field inside 0, but you see what you've done to the electric field outside. Now it's a big mess. And look, again, which brave particles is responsible for all that? Electrons. You see, electrons now travel to this side of the metal, leaving behind positive charges over there. So pretty much redistribution of charges inside of this metal guarantee electric field inside 0. Right, so it was all done by electrons. And also you see electric field just outside of the conductor, perpendicular. You see, at every point, electric field is perpendicular, like what we discussed in the previous lecture. Right? So now, as I said, now you can put any piece of equipment inside, and it will be safe from influences from the outside world. Actually, now there are some companies sell some, I don't know, containers, boxes for cell phones for people who don't want to no, want to protect their cell phones from being tracked, right? I found in the internet a few examples, right? So you see this guy is standing inside of the Faraday's cage, right, mashed. You know what? I would never do anything like this. Yeah, to some extent, I know physics, right? Trust physics, laws of physics, but I don't trust myself because I can forget about something, right? And I don't want to be zipped, right? So no. Nice picture, but I would never do anything like this, right? Then instead of building some cage, right, or solid piece of a metal, now there are fancier ways of sort of building Faraday's cage. For conductive fabric can be used. I know conductive plastics can be used, right? Or conductive paint. For example, the box inside can be painted with conducting paint, right? So, yeah, there are ways. Again, it depends on how strong electric, electric fields um, from which you want to protect your equipment. Right? Of course, it all has to be calculated. Okay, so very important application. Now, next step in making system more complicated. Again, you still remember we're studying properties of conductors, right? So first there was no holes, now we added a hole, and now how can we make the system more complicated? Let's put a charge inside of a hole, inside of a void, which is inside of the conductor, or something like this. And again, let's assume that this piece of a conductor is charged, right? Charged plus Q, total charge inside of the conductor plus Q. And there is a void, there is a hole, right? And inside I will dump, for example, positive charge Q. And now the same question. We know that excess charge cannot be inside of the conductor. So excess charge can be either on the exterior surface or interior surface. Actually, so far it was only on the exterior surface. And now the same question, logical question: is it possible in this case to have any excess charge on this interior surface? But in the previous slide, when we did not have a charge inside on the interior surface, there was no any charges. What about now? Yeah, you see, the same question. I just copied and pasted from the previous slide. And again, guess which law we're going to apply in order to answer this question. Again, Gauss's law. Gauss's law. And again, I will pick a Gaussian surface, which is going to be just above this interior surface, right? Just barely above or just barely below, right? Gauss's law. And now if I ask you a question again, what will be the value of this integral? You can tell me immediately, right? I'm sure that 100% of you now know the answer. What will be the electric flux to this Gaussian surface? It will be zero, because this surface is still inside of the conductor. And again, we tacitly assume that we waited for a short period of time to make sure that this conductor is in the electrostatic equilibrium. So electric field inside is zero, right? Electric field is zero, and so flux is also zero. So it means what? It means that Q enclosed must be also zero. Q enclosed must be zero. But in this case, we already know that there is this positive charge plus Q inside of this Q enclosed, part of this Q enclosed. So we know that one part of this Q enclosed is plus Q. It means what? And Q enclosed equals zero. So it means what? It means somewhere else there must be negative charge minus Q, right? To make Q enclosed zero, total charge zero inside of the Gaussian surface. And where can that charge be? There's only one place on the surface of this interior surface. Right. Again, excess charge cannot be inside of the conductor, right? And plus, we position Gaussian surface just below or above this interior surface, right? So that's basically the proof that in this case, if there is a charge inside of the conductor, in this case positive charge, there will be equal. Okay, there will be minus Q charge distributed somehow on this interior surface. So the total charge somehow distributed on the interior surface, the total charge equals to the charge inside of the hole. Distribution of the charge can be complicated, but the total charge on the interior surface is going to be in absolute value the same as charge inside, but with opposite sign. If I position here minus q charge inside of the hole, on the interior surface, we would have plus q. The total charge on the interior surface would be plus q, right? In simple words, right? So how can we sort of justify that conceptually, right? So this positive charge q attracts electrons in the conductor, because conductor has tons of free electrons. Of course, they feel attracted to this positive charge, and of course they fell in love, and of course they run towards that positive charge. But of course they cannot reach it. Of course they will get together on the interior surface. In a fancier way of explaining it, because this positive charge, right, creates electric field, its own electric field everywhere, and of course inside of the conductor. But you remember what's the response of electrons inside of the conductor? They will start running to make electric field inside of the conductor zero. So you remember they will redistribute themselves in such a way so that the electric field inside of the conductor is zero. They bravely protecting zero electric field inside. So they will come to this interior surface to make electric field inside zero. Right. So remember, on the interior surface, if there is a charge inside of the hole, there will be the same amount of charge on the interior surface, but with the opposite sign. Okay, we will use it. All right, and yeah, you will use it in your homework, so we need to remember this. So now, next question. So we know on the interior surface there will be this minus q charge. Then how can we calculate the amount of charge on the external surface? We know what? Again, so we know that the conductor is charged with plus q. So the total charge inside of the conductor, inside of the conducting material, this positive charge plus q small is not part of the conducting material. It's outside, it's in the vacuum, it's in the hole. So this plus q capital, it's a total charge inside of the conducting material, right? So originally it was charged, and now we know that minus q small is going to be on the interior surface. And now, logical question: what will be the charge on the exterior surface? And in order to answer this question, we need to use conservation of charge inside of the conductor. We assume that there is no leakage right through air of this charge plus q. So the total charge inside of the conductor all the time must be plus q. And we know that there are two places where this charge can be: exterior surface, interior surface. Because again, inside of the conductor, it's impossible to have the excess charge. So as a result, I can easily write conservation of charge. The where is it? Here. So the total charge plus q inside of the conducting material consists of two parts again: charge on the outer surface, which we want to find, and charge on the inner surface, which we just found. Again, there are two places where charge can be, either on inner surface or exterior surface. So here's the interior surface, here's the exterior surface. If you add them up, you must end up with the total charge. It's like, let's say you have two rooms, right? A two-room apartment. And you know that, I don't know, 10 people is in the apartment. So if you add the number of people in first room plus number of people in the second room, you must end up with 10. If here you found 4 people, then you can say with 100% accuracy that there will be 6 people in the second room, right? So that's what we have here. That's what I just applied. It's not a rocket science, it's simple algebra. So, and now we can solve for the total amount of charge on the outer surface. So you take this minus q to the other side, and of course you will end up with total charge on the exterior surface, on the outer surface, is Q capital plus Q small. Okay, right now it might be confusing. We will look at another example on the whiteboard. Actually, it's a problem from the book, right? Because very similar problems will be in your homework, and I tend to give a problem like this on the exam among multiple choice question. Once you get the logic, it's a piece of cake, right? Just the algebra. So now. So we will practice one more example about this. And now I think it's a clicker question. Yeah. Again, I created two clicker questions in the chat. So number one, I doubt that we will be able to get to number two, but just in case, I created both. Okay. Now let me open the conceptual question. So you see, we have a piece of metal, electrically neutral, so excess charge is 0. Then there is a hole, void, and inside of that hole there is a positive charge plus 3 nanocoulombs. Basically what we just discussed. And the question is, what will be the total charge on this exterior surface? Right? Okay, give it a try. And then we'll start solving problems on the whiteboard, I think, after this. This distribution of answers are more encouraging because at the end of previous class, it was a little bit depressing. Right. Laugh reaction. Cool. I'll just start discussing. Okay, so analysis is very simple. Basically, it's like in the previous slide. So if we have positive charge plus 3 nanocoulombs in the hole, of course, negative charge minus 3 nanocoulomb will be induced on the interior surface. So negative charge, okay, I need to bring slides forward again. So negative charge minus 3 nanocoulomb will be induced on the interior surface. Right. Again, distribution of these negative charges will be somewhat complicated. It depends where this charge plus 3 nanocoulomb will be positioned. But we can tell for sure that the total amount of charge on the interior surface will be minus 3 nanocoulombs, right? And then, since the total charge inside of the conductor is 0, conductor metal is electrically neutral. So it means that if we have minus 3 nanocoulomb on the interior surface, plus 3 nanocoulomb must be on the exterior surface. Right. Just verbally, I applied conservation of charge. Q on the outer surface plus Q on the inner surface must be equal to 0 because metal is not charged. It's electrically neutral. And we have just found amount of charge on the interior surface minus 3 nanocoulombs. It means Q on the outer surface must be plus 3 nanocoulomb, right? So logic is basically trivial, right? And of course, we used fundamental law conservation of charge. And conservation of charge of the conducting material. This charge plus 3 nanocoulomb is not part of the conducting material. It's outside. It's in the vacuum. It's in the hole. Okay, so minus 3 and plus 3 nanocoulombs, right? Okay, so the answer, of course, is B. And most of you answered that right. So next, it's basically the same thing, but now you can have, for example, two voids. And if conductor is electrically neutral, pretty much the same logic can be applied. First, you find the total charge on this interior surface, then on that interior surface, and then apply conservation of charge. Now, excess charge can be on the exterior surface and interior surface number 1 and interior surface number 2. Logic the same, but you'll have a larger number of terms, right? But again, it's just a simple algebra, right? So let's assume that we have a piece of conductor, and that conductor is charged. Again, that is excess charge, additional charge, which we dumped in the conductor. Okay, let me draw some arbitrary shape conductor. So let's say that is my conductor, right? So, and I can maybe even show that this charge is inside of that conductor. Okay, but it's not enough. Let's make a hole. Let's make the situation more complicated. So I will make a hole over here of some complicated shape. And so conducting material, let me show it this way. Okay, so that's a conductor. And that is the hole. And let's make situation more complicated. Let's dump charge inside of the conductor. Q sub H. H stands for hole. Right, so I decided to label it this way. All right, so this will be our QH, right, which is plus 100 nanocoulombs. I feel like writing this number next to the charge. Okay, so that's the situation, electrical situation, and logical question. What will be the total amount of charge on the interior surface or inner surface? And what will be the total amount of charge on the exterior surface or outer surface? So first, okay, I'm going to label them just as Q inner and Q outer. Okay, and of course, I mean by outer, it's a surface, right? So these are two questions. Questions like this, quite often I give among multiple choice questions on the final, on the exams, on one of the exams. Okay, but of course, after discussing our slides, it should be straightforward, right? What about Q inner? You should be able to answer that question immediately, right? So Q on interior surface must be equal to the absolute value equals to this charge, but with opposite sign, right? Again, basically, this positive charge is going to induce negative charges on the inner surface, right? Or attract electrons, right? Electrons will run to this surface to make what? To make electric field inside of the conductor zero, right? So that's the reason for appearance of this negative charge on the inner surface or interior surface. And so it just will be minus 100 nanocoulombs. Again, if somebody says, no, I don't believe it, okay, grab Newton's, grab Gauss's law, right? Introduce Gaussian surface just above that surface, apply it, see that Q enclosed equals 0. And since we have already one charge inside QH, there must be other charge somewhere with opposite sign. Gauss's law can prove that, right? But I usually don't demand proof on the exam. I just want to see if you see this effect. So then, next, Q outer surface. And now we're going to use, as I told you in the lecture, conservation of charge. Conservation of charge, and I will add in the conductor. Again, in the conducting material. Conservation of charge, and I will emphasize in the conductor. Right. And as we already proved that excess charge cannot be inside of the conductor. It just God created nature this way, right? And we're just trying to describe it, right? In our using our humble tools, or maybe not so humble, right? So we know the charges, excess charge can be only either, in this case, exterior surface or interior surface. Like I compare it with 2-room apartments, right? So you know if 6 people over here in this room, 4 people must be there. So it means that here we have, this is total number of people, total charge, and this total charge can be in 2 places. One room, outer surface, the second room, inner surface. There are only 2 places. All right. So we can write conservation of charge just trivial. So I can write, so Q total, that one, equals Q inner plus the total amount of charge on the exterior surface, right? And this is given, oh, yeah, it's given from the very beginning. Q inner we just found, and that is our unknown, right? So we can solve it, of course, easily. Q outer will be equal Q total minus Q total amount of charge on the interior surface. Now plug numbers. So total minus 50. Okay, let me write underneath. So it will be minus 50 nanocoulombs. Then minus from the formula. And the value of the inner charge is negative self. So there is a second minus. Be careful with minuses over here. Sometimes I see students make silly mistakes losing these minuses. So it will be, oops. Okay, there was a problem with the power. I hope internet stays. Guys, are you still there?
Yes.
Awesome. Because you saw, right, there was a problem with electricity. Okay, now I'm scared that we can lose the class. Okay, so minus 50 nanocoulombs plus 100 nanocoulombs, of course, you will end up with plus 50 nanocoulombs. That will be the total amount of charge distributed somehow. Of course, distribution of charges on those surfaces will be complicated. We can tell only about the total charge. Right? So plus 50 nanocoulombs. So let me draw this 50 nanocoulombs on the exterior surface. Let me draw a few pluses. So that's Q outer. And inner surface over here, of course, negatively charged. Okay, based on my experience, some students confused about this point. Okay, just recently we used Gauss's law a lot, right? And every time in the Gauss's law, we count, okay, you pick a Gaussian surface, and of course, then we counted all charges inside of the Gaussian surface, right? And so they developed a habit of counting all the charges. And now over here, we have this charge inside of this void, inside of the hole, and now we're not counting it in this conservation of charge. And some students feel not very comfortable at all, so they confused. So how come in that law we count all the charges, right? So inside, and here in conservation of charge, we're not counting. Guys, we're trying to apply two different laws. Gauss's law and conservation of charge. They have nothing in common. They're just two different laws. And according to the rules how you need to apply Gauss's law, we need to count all the charges inside of the Gaussian surface. That's how we apply that law. According to the laws of conservation of charge, and in this case I want to keep track of all charges inside of the conductor. This charge Q hole is not part of this conducting material. It's in the vacuum, it's outside of the conducting material. So we just have two different laws. They have nothing in common except for they belong to the same world of electricity. So I'm just telling you the common place for confusion. We just need to apply. It's just everywhere, right? So in physics, we introduce a new law and then we learn rules how to apply it, right? What can be used, what can be done, and what is wrong. So you just need to remember, right? So if it's a Gauss's law, yeah, count all the charges inside. But in this case, this charge QH is not part of the conductor. So that's why it is not in this equation conservation of charge. Clear? Because I get this question almost every semester. So gaining experience and trying to clarify all the possible places for confusions. Okay, so very similar will be in your homework, right? And after this, you shouldn't have any issues except for be careful with moving terms, which charge is positive, which charge is negative, because okay, not very easy, but I see sometimes students make really silly mistakes, and then they come to me after exam. I know this, but I just wasn't very attentive. I didn't uh, do my best and lost some sign, right, and so on. So otherwise, it's not a rocket science. Even rocket science is not a rocket science. It's just everything is reasonably straightforward. All right. But again, guys, if you need some additional explanations, tell me. All right. So meanwhile, let's start discussing the next problem, 36. And actually, I think this problem is part of your homework. I usually assign it so that students can just practice by themselves at home. So what do we have here? A hollow metal sphere. Again, conductor, conducting sphere. So we have a solid sphere, and inside there is a concentric hole. Okay, I prepared this picture in advance. So you see, external radius B, external surface, right? Then there is a hole of radius A, and again, this is metal. This is piece of a conductor, and that piece of a conductor is charged. Now positive charge plus 2q. Then, to have more fun, let's add positive charge plus q inside. Basically, it's similar to that, but yeah, their charge was negative, and the question is about a different question here. There, we just trying to find the amount of charge on surfaces. In this problem, we want to find expressions for the electric field everywhere. We want to find electric field here outside, inside, and inside of the hole. So we need to find 3 expressions for the electric field. Yeah, I wrote find electric field everywhere. And so obviously we'll have to find electric field in 3 regions. So let's do it. First let's label them. Let's label them. And I'll probably use blue. So I will start with region 1. It's inside of the hole. Then inside of the conductor region 2, and region 3 will be outside of the whole structure. So let's start with region number 1. All right, so let me put A, and we need to find electric field in the region 1. It's absolute value. At this point, you should be able to guess which law I'm planning to use. Because we have nice spherical symmetry, it's a clear indication that Gauss's law will be pleasant to use. It will be a piece of cake, right? So we're going to use Gauss's law, right? So we're going to again write integral over the closed surface E dot dA equals to Q enclosed over epsilon naught. And it's a spherical symmetry, so basically steps will be exactly the same like the steps we've applied 2 classes ago, when we applied Gauss's law to find electric field inside of the uniformly charged sphere and outside of a uniformly charged sphere. Exactly the same steps. But again, first of all, we need to pick a Gaussian surface. And the Gaussian surface must be in the region where you want to find electric field. So it's here. Right. So of some arbitrary radius r small. Right? And of course, you can draw electric field, area vector. Because of the symmetry, of course, electric field will be radial. So all those steps which we discussed. So now, of course, I'm not going to be as thorough as I was back then. So that's Gaussian surface. Let me even show that that's our Gaussian surface. And right, so I can make exactly the same steps, right? Okay, let me write in this part. So of course, first, electric field is in the same direction as the area vector. Of course, this integral can be rewritten as EdA, right? Vector signs disappear. So now we have a product of two magnitudes, because again, angle between these two vectors is 0, cosine of 0, 1. So we're getting that. And so now, because of the symmetry, it doesn't matter where you are on this Gaussian surface, electric field strength must be exactly the same, because from that point, if you look from any point on this Gaussian surface, distribution of charges which create electric field strength exactly the same. So it's a clear indication that electric field, again, electric field strength is constant. So I can continue. So I can write, since E is constant on the Gaussian surface, so I can extract that out of the sign of integration. So you see, steps are the same. And again, it's a calculus 3 integral, but we know the answer. 4 pi r squared, r small. So it will be 4 pi r small squared. So of course, the answer, the value of this flux will be E times 4 pi r squared. And from the other side, it is equal to Q enclosed over epsilon naught. So that's what we got. You see the same steps. I just moved much faster. And so what's the value of Q enclosed? At this point, everyone should be able to see, right? So inside of this Gaussian surface, there is only one charge plus Q capital. So plus Q, and as a result, I can write immediately, so this equals to plus Q, and we can solve it for the electric field. Of course, I can write it as a function of R. So as a result, E as a function of R equals to 1 over 4 pi epsilon naught. Okay, I can put Q upstairs, and downstairs will be R squared in the denominator. Right. So that's the expression for the electric field inside of the hole. Right. So it's just created by the point charge, effectively. You know what? I should add here, at least in the answer, it's region 1, E sub 1. Right. Okay, so now second region, B. So E sub 2. Okay, who can tell me the answer? What will be the answer in part B? Can you see that? Okay, I see the responses in the chat. Exactly. It's like at the end of the previous class when I saw your answers, I was really somewhat depressed, right? But okay, now I see that you're getting it. Of course, region number 2 is inside of the conductor. And of course, once you dump this charge, once you position this charge plus Q at the center, you wait for a short period of time, maybe microsecond, maybe nanosecond, maybe picosecond, right? Who knows? It depends on the mobility of electrons and so on. But you wait it long enough so that this conductor reaches what is called, again, the electrostatic equilibrium. And once conductor in that state, electric field inside of the conductor must be zero. Electrons will do whatever it's needed, but they will make electric field zero. Otherwise, they will never stop running. Right? So electric field in the second region is zero because it's a conductor. So in this case, we didn't have to do anything. We don't have to do anything. So E2 equals to zero, and I will emphasize inside of, okay, the conductor. Okay, let me frame it. So that's the second region. And now the last one, the third one. So A, B, C. So we need to find electric field in the region number 2. Now we are not in the conductor. Now we are in the vacuum, right? And of course, electric field cannot be zero because there are conductors charged, plus inside of the hole there is a charge, right? So there will be a more complicated picture. But we know how to handle that. Gauss's law, because we have nice symmetrical distribution, so application of Gauss's law will be probably the most pleasant experience, right? All right, and of course you remember Gauss's law in general is the fundamental law. You can apply it to find the electric field of any electrical system, any. Right, so again, Gauss's law, I will just write electric field, integral E dot dA equals to Q enclosed over epsilon naught. And again, first step, you have to pick a Gaussian surface. Again, the Gaussian surface must be in the region where you want to find the electric field, and of course it must match the symmetry, right? In order so we can utilize the symmetry, right? So it means that Gaussian surface will be somewhere out there, right? So over a Gaussian surface. Now maybe I can draw a big line. So that's our Gaussian surface. Of course, of some arbitrary radius r small, right? And again, this part will be exactly the same. So I will just write immediately E times 4 pi r squared. So it will be okay, yeah, let me E times 4 pi r squared equals to Q enclosed over epsilon naught. And what's the value of an enclosed charge? Okay, I'll give you a few seconds. Think for yourself. What are you getting? What will be the total charge within the Gaussian surface? Charged physically embraced by our Gaussian surface. It's again, it's straightforward, right? So I'm not trying to trick you, right? I'm just okay, some people think Q, right? Okay, think more. Be greedier. Why just Q? Grab everything possible. 2Q. No, be more greedier. No, you're not greedy enough. 3Q. Right. Okay, guys. Yeah, I convince you to be greedy. Right. Look, guys. That's why I posed, right? Because you need to start thinking. It's like when I was a student, right, in the university in Ukraine. I remember our professor, mathematical analysis. He would call somebody to the board he would volunteer somebody to the board, and a student would try to take an integral of some limits, right, or something else, right, or maybe some differential equation to the point, and the instructor would be just sitting and watching, right, till the student gets stuck somewhere, right? Then we would start helping that student, right, trying to show him the direction, right? And then we will all get stuck, and then the instructor would say, okay, erased up to that point, and after that he would start guiding us, explaining where we made a mistake, what was wrong, what's the better approach. So at that time when we got stuck, our brains were active, really active, and we were just actively searching for a solution, right? So at that moment, of course, it's much easier to accept the correct directions, right? Okay, so Q enclosed, again, just by definition, what is enclosed charge? It's a total charge physically embraced by the Gaussian surface. So let's look. Gaussian surface is here. So we just need to count all the charges inside. Let's start from the very center. Definitely plus Q is there. So it must be counted. No charge left behind. So that should be a slogan, right, of this counting. No charge left behind. So plus Q. Then, of course, like what we discussed over there, some charge will be induced on this inner surface. Some charge will be left behind on this outer surface. Like we can apply this logic, like that logic, in order to find that amount of charge. But do we have to do it here? Do we have to do that here? Because we know that the total charge inside of the conductor plus 2q, so charge on the outer surface plus charge on the inner surface, will be equal to plus 2q. So all that charges is inside of our Gaussian surface. Of course, it's not bad. You can find the total charge on the inner surface, on the outer surface. You add them up, and of course, 100%, I can guarantee that you will end up with charge plus 2q. And you remember in the Gauss's law, when I introduced Gauss's law, I told you that distribution of those charges inside of the Gaussian surface doesn't matter for the Gauss's law. Right, you remember I told you I can grab this charge, move it slightly or maybe not so slightly, as long as that charge within the Gaussian surface counted in. All right, so yeah, some charge will be on the outer surface, but it's inside of the Gaussian surface. Some charge will be on the inner surface, but again, it will be inside of the Gaussian surface. And we know the total charge of the conductor plus 2q, so I don't have to do that. I can write immediately plus 2q. See that point? So it will be plus 2q. So it will be equal to plus 3q. The logic is simple. But of course, we need to know how to apply these laws, right? Right. If you're still confused, tell me. Okay, so we just need to plug it and solve for E. Okay, I will write immediately the answer. So E in the region number 3 as a function of R will be equal. So this is plus 3q. Then divided by 4 pi epsilon naught times R to the power of 2. So that's the answer for the region number 3. So problem is solved. But of course, if on top of finding electric fields, you want to know what's the amount of charge, total amount of charge on the inner surface or outer surface, yeah, we can apply this logic like we've done it over here. And you can do it quickly just in your head now, right? So since inside of the conductor there is a plus q charge, of course, on this interior surface there must be minus q, right? And then the next step, you apply conservation of charge. The total charge plus 2q. Inner surface we just found minus q. So it means that on the outer surface there must be charge plus 3q. So plus 3q minus q, it will be plus 2q, right? So it's this plus 2q. So q in the hole plus 2q inside of the conductor, 3q, right? Oh, somebody thought 3 to the power of q to the power of 3. No, that's too much. That's too much. Right. Okay. I already broke part of my marker holder, but it's still alive. And from now on, guys, on the exam, read carefully which material is given in the problem, because I saw in the past when I give just a non-conducting material full of charges, right? For example, sphere, and I ask to find the electric field, for example, inside, like dielectric material charged. And find electric field inside. And some students write, okay, inside the right electric field equals 0. No, 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 no. Electric field like here equals 0 only if your material is a conductor. But if the problem says a non-conducting material or dielectric material charged, right? So this is wrong for those cases, right? So it is only correct for conducting material. So read the problem carefully, which material is there.